the molecular orbital diagram for N2, nitrogen having the electronic configuration of a helium core, 2s2, 2p3, therefore this is giving us 5 valence electrons. Molecular orbitals will form between the two s's of the nitrogens, forming the sigma 2s bonding and the sigma 2s antibonding orbital. There will be bonding between the 2p in both nitrogens, forming the pi bonding for the 2p and the sigma 2p bonding orbital, which is at a higher energy than the pi bonding orbital, which only occurs in carbon, boron and nitrogen. We then have the pi 2p antibonding orbital and the sigma 2p antibonding orbital. Now we have 2 electrons in the 2s of both nitrogens, so 1, 2, 1, 2. They will occupy both the bonding and the antibonding orbitals. In the 2p there are 3 electrons, 2, 3, and we must assign them appropriately following Hund's rule, which says that electrons must be unpaired and be parallel before you can pair them up, as this will maximise repulsion. We then have 1, 2, 3, 4. We now have 2 left. We pair them up because they must go into the lower energy shell before they go into the higher energy. This means that we have a bonding cancelled by an anti-bonding. We then have the sigma 2p. We have a pi 2p and a second pi 2p. This means we have one bond here, a bond here, a bond here. This is a triple bond. And the Lewis structure of N2 appears as so, with we have 1, 2, 3, and we know that a triple bond must be a sigma bond with a pi bond and a pi bond, as is demonstrated here, sigma 1 pi 2 pi. The molecular orbital diagram for carbon monoxide. Now, carbon has the electronic configuration of having a helium core, 2s2, 2p2. Oxygen has the same helium core with 2s2, 2p4. This gives us 4 valence electrons, 2 and 2, and for oxygen we have 6, 2 and the 4. Oxygen is much more electronegative than carbon. Oxygen's 2s orbital is so electronegative at 32.3 electron volts there will be no bonding between the 2s or the 2p of the carbon. However, oxygen's 2p subshell sits at 15.9 electron volts between the 10.7 electron volts of carbon's 2p and 19.5 electron volts of carbon's 2s. This skewing in the molecular orbital diagram is due to the difference in electronegativities of carbon and oxygen. This gives rise to the 3 sigma bonding orbital, the 4 sigma bonding orbital, the 1 pi bonding orbital, and the 5 anti-bonding sigma orbital. It will give 2 pi antibonding orbitals and the 6 sigma antibonding orbital. The contribution to the 3 sigma bonding orbital is exclusively from the 2s of oxygen, 1, 2. The 4 sigma bonding orbital takes 1 electron from the 2s of the carbon and 1 from the 2p of the oxygen. This leaves us with 1 electron in the 2s, however it must bond up here, but we'll come to that later on. We then start looking at the 1p. Well, we have 3 electrons remaining in here. So we're going to go 1, 2, 3. Now we have this paired and this unpaired. We are now use all the electrons in oxygen's 2p. We then move up into carbon's 2p. We then bring this one into pi's, and then we have one remaining 2s here, which can bond into the 5 sigma antibonding, and we have the remaining electron in here in the 2p that can make its way down to the 5 sigma antibonding also. This results in having 1, 2, 3, 4 bonding orbitals and 1 antibonding orbital. This leaves us with 3 bonding orbitals representing 3 bonds. This is the same as nitrogen, having 3 bonds, nitrogen being as so, and explained earlier. Carbon will have a triple bond with oxygen. Due to the difference in the number of electrons that carbon has and oxygen has, there is not an even contribution to the bonding between the two atoms in carbon monoxide as there is between the nitrogen and the nitrogen in N2. That is how the two molecules differ, other than having the triple bond and obviously different nuclei. Molecular orbital diagram for O2 2+. So oxygen has the electronic configuration of a helium core, 2s2, 2p4, and this would form O2, but we're dealing with O2 2+, which means that we have 2 oxygen plus ions. So we'll be dealing with He core, 2s2, 2p3, going from 6 valence electrons to 5 valence electrons that we use in the molecular orbital diagram, 5 for each O+. Due to O2 2+ being formed of 2 O positive ions, and here we have the 2s, and up here the 2p, and the same with the 2p here and the 2s here. Now we have 2 electrons in the 2s, so we have 1, 2, 1, 2, and we have 3 in each of the 2p's, 1, 2, 3, all unpaired, because Hunt's rule says that they must be unpaired and run parallel before they pair up. Down here we will have the overlap between the 2s subshells and their single orbitals to form the sigma 2s and the sigma antibonding 2s orbital. We then have the overlap between the two p's here, first off at the bonding 2p or sigma 2p. There will then be overlap to form the pi 2p bonding. This will also then have pi 2p antibonding and sigma 2p antibonding. Now when inputting the electrons, one from this 2s and one from this 2s, 1, 2, leaves us with 2 remaining, so both the bonding and antibonding are filled. We then put 1 electron in for both sides into the bonding 2p, 1 each, 1, 2, leaving us with another 1 left on both sides. In they go. The similarities between O2 2+ and N2 are such that the bond orders are both 3 due to the antibonding present in both the 2s. Therefore we have 2 pi bonds and a sigma bond between the 2 parts of the O2 2+ molecule, between both the O positives. And in N2 we have 2 pi bonds and the sigma bond between the 2 nitrogens that form N2. However, the differences arise at the sigma bond in O2 2+ being at a lower energy than the pi bonds, whereas in N2 the sigma bond is at a higher energy than the pi bonds due to carbon, nitrogen and boron all having this trend. The bond order of O2 can be calculated from having 8 bonding minus, let's say 4 over 2 equals the bond order of 2. 8 minus 2 over 2 equals 3 equals the bond order. There is less antibonding present in O2 2+ molecular orbitals than there are in those of O2.